recap. First week, we did some review. We did an introduction to calculus, and at the end of class, we started working on limits. And that's mostly what we're going to look at today. I just want to say, by analogy, I asked you guys to build a house, and I showed up with some lumber and some nails. You say, that's great, but we need some tools. And we're going to get some tools today for doing limits. But, you know, the more curious of you might want to know, well, how do you make a hammer, right? And not everybody's interested at that level. We just want to get the house done. But we're going to take a look in a couple minutes. We're going to take a look in a minute. So, you are... Quasi.
Yeah.
Okay, so here's the catch, Quasi. You can sit there today, but someone else wants that seat. They're just not here. Or maybe they're dropping out. I don't know. This seat here and that one there are available. And, you know, if you want to be on the corner, you know, on the side, that's available, or in the back. So, I just don't want them to come in and get confused. Nice to see you. Okay, so let's just take a look at, again, at this idea of a limit. We have some function. Be consistent. We have some function, and we have some x value, I'm going to call c, which is possibly a value to the function, it might not be defined. And we're interested in values of x near c, and what value of the function you get near c. So we don't really care what f of x is at c. In some cases, it will be our limit. It doesn't have to be. It could be a different value, or it could be, the function could be undefined. So that's what we're interested in here. And we're going to look at a very formal definition of a limit. I think we just we're starting to look at this. I made a mistake on Thursday. As I said, I will make mistakes. For some odd reason, this is a definition. And I said it was if and only if, and that doesn't, definitions aren't if and only if. Definitions are just if. So my definition is the limit is x approaches c with f of x equals L, the limit, if the following is true. Each small number, which we call epsilon, greater than 0, there exists a delta greater than 0. I don't know, people familiar with this notation? There exists. There's a similar notation you might use for all x. That was mine. So for each small value of epsilon, which is going to be a number bracketing our limit, right? In other words, from L minus epsilon, L plus epsilon. For each such epsilon, there's a delta such that this is where it gets a little complicated. If x is in here, which I'm going to write out this way, x minus c is less than epsilon but greater than 0. In other words, I'm saying if I have some x on this interval here that I'm interested in, it's really small interval, then, well, I'll explain what this means in a second. F minus L is less than epsilon. Oops. Sorry. This says if x is in this interval here, yeah, I got this wrong, sorry. All right, try again, Mitchell. You do good. X minus delta plus delta. Okay. So if x is in here, I want f of x within that epsilon you give me. Yeah. All right. This is actually a pretty complicated idea. So we're going to go over it for a minute or two, just so you get a feel for it. Let's say my f of x is x squared, and my c is 1. And let's say my epsilon, I say my epsilon is 0.1. So what does that mean? Okay, so c is 1. I want all x's between 0.9 and 1.1 when put into x squared. I did it again. I'm switching my epsilons and my deltas. Here's my limit, 1.1, 0.9. So I want my function squished between these values. You know, what value of, well, I guess I should go in here. So I want to say the limit as x approaches 1 of x squared equals 1. Right? So I want to squish, I want to squish my function values between here. Can I find a delta that does that? Well, you could just, you could look at it and say, well, you could just pick a really small number, right? If delta is like 0.001, I know that 1.001 or 0.999 squared is going to be between 1.1 and 0.9. That's kind of what we're doing here. Now, there's nothing wrong with picking a delta that's kind of, better than the minimum, right? I could just as well pick delta and put a few more zeros. The key is I have to be able to pick a delta, given any epsilon, any small number. Okay, now, I really want this to just be a conceptual idea. We're going to do a little bit of the mechanics of it, but that's not what's important. I want you to think about this. I have some function, and it's getting close to some number we call the limit. And I can just say, well, how close do you want it? Do you want it 0.1, 0.01, 10 to the minus 100? However close you want to get, I can give you an x a range of x's near C that squish it into that. That's the idea here. Now, if you think about that in your head, and then you think kind of, you do something you can only do in your mind. You can think of like infinity, right? You can just make that tiny small amount smaller and smaller and smaller, and smaller and smaller and smaller. You can get as close as you want. And your function just, we can get your function that close. But keep in mind, it doesn't, you might think, well, why not just plug in 1 here? Right? I mean, we will do that later. But in some cases, you can't do that. But you still have a limit. And we'll look at some examples of that today. So, I want to let that sit for a minute. See if you have any questions about it. I guess I want to digress for a second. Nobody, yes?
I'm having trouble following the examples, the numbers that you use. Why does it go 0.9, 0.1, 1.1?
This number?
No, on the graph.
Oh, on the graph.
The epsilons.
Okay. So, think of this as a conversation, right? I claim that this limit is correct. The limit as x squared, as x goes to 1, then x squared gets close to 1, right? You say, well, I'm going to give you a limit of 0.1, an epsilon of 0.1. I want you to be within 0.1 of x of 1. My job then is to give you a range that will force that to happen. All right, so you can give me a smaller number, let's say 0.01. But for every possible epsilon you could give me, I have to be able to produce a delta. That's what makes this a limit. All right? We might have a function where you could give me an epsilon, I could give you a delta, then you give me a smaller epsilon, and I can't anymore. And then it's not the limit.
So that 0.1 isn't that's not like a value, that's how far away from the value you want it to be?
I want it to be, no, I mean, I want the limit to be within this range of values. In other words, what a limit is as I get close to x, as x gets close to c, my function gets close to the limit.
Which is 1.
Which in this case happens to be 1.
But you want it to be within 0.1 of the limit.
I've asked, yeah. In this example, I said, make it within 0.1, and I can give you a delta. I can give you many deltas, but I just need to give you 1. If you give me a smaller number, can I still give you a delta? Or if you want to play devil's advocate, is there an epsilon so small that I can't find a delta that squeezes the values in that range? If I can't, it's not a limit. It's not the limit. Different question would be, well, is there a limit? Yes?
I think I'm just a little confused the units that is going in for the epsilon. So is it 0.9 bigger than 0.1?
Yeah, that's what I was asking too.
Yeah, so.
I said the tolerance is 0.1.
Yeah.
So it's around 1, but the 0.1 is up or down.
Yeah, 0.1 is like a range.
So if it's 0.1 or out of 0.1, then would it be 0.2?
There it
And
is.
then it would be.
This is, these values are f of x, right? So what we want is, as we get close, as x gets close to 1, we want to see that f of x gets close to 1, coincidentally the same number. right? But we can't actually require that f of x be 1 at 1. In fact, we don't even care what it is at that. Let's say I define f of x this way. F of x equals x squared for x not equal to 1, and 5 for x equal to 1. So the way that looks is I have a little hole here, and I have a point up here. The limit of x squared, as x approaches 1 of x squared, is still 1. It's only that one point that's kind of a problem. But because we can get as close to that value as we want, as we move towards 1, it's a limit. It's kind of a weird idea, and you'll see why we need this coming up. We need this for calculus. Yes?
Is it the idea that you can split things in half for an infinite number of times before you redo that as a concept?
You could split it in half, or you could divide it by 3 or 5. Keep doing that. Yes?
And you've never actually reached the point.
You've never reached the point, no. No. Yeah, you have to think about this. You have to kind of take it in a little. Yes?
Are you going to say cost split an example?
Yes.
Step by step?
Yes, we're gonna. This is the conceptually difficult part to figure out. So I am, letting you just sit and think about it a little. Once we get into the mechanics, this is going to be very easy. Yes.
So in order for a limit to exist, you need 2 points conceptually. Because if it can't be 1, so that'd be 1 point. So it'd be, if it's 0.9, it's 2 points. Right?
I want to get to what you're thinking about, but I want to say something first, right? In order for you to have a limit, I didn't really say this, the function has to be defined near the point, all right? If we were to have a discrete function, if 1 is 1, 2 is 2, this is kind of like x equals x, 3 is 3. And I said, what's the limit as we get close to here? The limit is not defined because you need the function defined near this point. So you need more than 2 points, is what I was trying to get at. Now, if you repeat your question, I'll try and, I guess in a sense you have x, and you have, we'll say x plus or minus epsilon, right? And I did it again. You have the limit plus or minus epsilon. So you have kind of, it's not just epsilon, it's in a way, it's every point further away. If we're within epsilon if we want to be within epsilon of the function, we have to be able to pick an interval that will always, all the points within that will fulfill that requirement. This is heavy duty stuff. We don't usually give this, well, we don't pursue it in calculus. It's just, it's the starting point. And we do need to understand how to deal with limits.
Is it in the textbook?
Yeah, you can read the textbook. I guess I want to in general suggest that when we go over a section, before you do the homework, you might want to, at the very least, scan it because maybe there's something you forgot or there's some detail I left out. But you're always encouraged to take a look at the book. You're also encouraged if you see something in the book I can go over and you have a question, bring it into class too. It's an open season on Professor here. All right. I'm going to do one formal example of this for you. Not to confuse you, if it doesn't all kind of fit together, that's all right. I should have up there. Limit. Were you to take calculus a few decades ago, or if you were a math major, you might spend a lot of time doing problems like this. I'm just going to give you one, a very simple one, and I think everybody can follow this. So we want to show something that on the surface looks very obvious. We want to show as you get close to 2, this function 2x minus 1 is close to 3. It's not an issue of whether the function at 2 is 3, that we know. It's how do we show that as we get close to it, we're getting close to 3, this limit. All right, so I guess I'm going to draw a little diagram here. It's going to look like this. There's a point here. That's where 2 is. And this just happens to be where 3 is. Okay, so what we're concerned about is you provide an epsilon, small number, and we want to know that our limit in this case minus that our function minus the limit is less than epsilon. We want to squeeze that in there. So let's write that out. Our function is 2x minus 1, and our limit is 3. So we want a delta. We want to find some delta so that if x minus 2 is less than delta, then this is the case. All right, so how do we go about doing that? Well, let's rewrite this here. This is 2x minus 4 less than epsilon, or we can take out 2. Or I'm going to rewrite this as x minus 2 less than epsilon over 2. All right, well that gives us a pretty good hint of what we want to set delta to. We can set delta to anything either less than or equal to epsilon over 2. We'll just say, let's set delta equal to epsilon over 2. Well, now we can just see that working backwards, we found a delta, epsilon over 2. We take our steps backwards, we have exactly what we wanted to show. But now we can squeeze 2x minus 1 minus 3 inside of epsilon. Right, so we have a delta that works for any epsilon. It's going to keep the limit within epsilon of that value. Right. This is how you formally do limit proofs. You prove something's a limit. You're not going to have to do any of these in class. We're just going to show you how to get around these. Okay. Before we do that, there's just a couple kind of technicalities, some oddballs that we're going to run into. I guess we'll put them over here. The first is, we'll come across this kind of situation. Limit as x approaches 0, square root of x, which in case you're not familiar looks like this. Square root of x. So the problem we have with this particular limit is that in this definition, you need room. You need a function which is defined on either side of our limit. But we don't have that here because x isn't defined for negative numbers. We're just dealing with real numbers now. So we have this concept, it's called a one-sided limit. And what it means is that instead of close to a point from either side, we're just interested in closing in on a point, on a limit, from one direction or the other. So we can make this a valid limit. We say x approaches, and then we use a little plus here, 0, meaning we're coming in from the positive side. And this is I guess this is a left-handed limit. We could just as easily have had some function which is only defined this way, in which case we would have a right-handed limit. And we would, let's say this is c, and this is some f of x. We would say the limit of f of x as x approaches c from the negative direction. That's what this negative here means. And then whatever that limit is. Now, I've introduced these one-sided limits as if you have to have this limitation here. You don't. You could have some function, and it has a limit. If it has a limit, it also has a left-hand limit and a right-hand limit. And in fact, there's a theorem that if the limit as x approaches c of f of x equals L, then the limit as x approaches c from the right is L, and the limit of f of x as x approaches c in the negative direction is L. So if you have a limit, both the left and right hand limits are limits. In addition, if you have both the left and right hand limit, that's sufficient to say that you have a limit. It's a detail. I don't know if Stuart goes out of the way to bring it up. I don't know if we're going to run into that. But you should be aware that you can have these one-sided limits. If your it's especially useful if your function doesn't continue like it does in square root of x. Okay, so that's one kind of technicality. we want to kind of enumerate them, but we've got a limit, we've got a left-handed limit, we've got a right-handed limit. We're going to have a few more. Look at the function 1 over absolute value of x minus c. Let's take a look at what that graph of that looks like. I have a value c here. And probably asked this before. There's a line here that the function, you know, we're getting closer and closer to it. Anyone recall the name of this kind of line? Yes.
The asymptote.
It's an asymptote. In particular, this is a vertical asymptote. And what we're interested in is the limit as x approaches c of f of x. Oh, well, wait a minute, what happens here? As we get closer on this side, it kind of goes off to infinity. As we get closer on this side, it goes off to infinity. Well, infinity is not a number, it's not a value. So a perfectly legitimate answer to this question is it does not exist. However, that doesn't tell you much. There are all sorts of ways limits may not exist. In this particular case, we have a term for this. This is called an infinite limit. That is, as you get close to c, from either side, your value of your function gets larger and larger without bound. Okay, that's just something we may run into. And we would write that this way. We would just say infinity. All right? Keep in mind, this is not a normal equality. It's not, you know, there's no number infinity. It's just, you can get as large a value as you want by getting close to c. Also, you know, recall, you know, what I've been saying about limits. It doesn't matter what the value is or if it's defined. This function is not defined at c, right? So we can't really talk about its value at c. All right. So, okay. Any questions on all this? Yes.
Can you define what an infinite limit is then?
An infinite limit occurs when, as you get close to the value, the function either goes off, you know, positive infinity, or it could, you know, we change this to a minus, we'd go to minus infinity. That would look like this. It's a specific, it's a terminology we use. If I showed you this and said, what's the limit? This is a question on an exam. A perfectly good response would be DNE, does not exist. It's not a limit in the sense of, you know, L equals some number. It's just a way of describing the behavior of the function near that point. Okay. Where was that? Erasing board. So we want to have some tools. I'm going to leave this up for a moment. We want to have some tools So when we're evaluating limits, we can do it, without having to come back to this primary definition. So the first tool I'm going to give you seems pretty obvious. Given f of x equals k, k is a constant, the limit as x approaches c of f of x equals k. This sounds like, this is really dumb, isn't it? And it sounds kind of dumb. We've got a function. It's a constant. We want to know what the limit is. What happens to this function as you get close to c? Well, I don't want to do too many of these because I don't want to upset people, but I really want to do an epsilon delta proof. Okay, so, given some epsilon greater than 0, choose delta equal to anything you want. Because this value, f of x minus k, is equal to 0, which is always less than epsilon. We don't really even need to pick a delta, really. Boom, we've shown this limit here. Again, that was so simple. Sometimes things that are really simple kind of go right past you. Okay. Let's add to our toolkit here something maybe more useful. F of x equals x, and the limit as x approaches c of f of x equals c. Okay. So here I have f of x equals x, and I want to know what the function, I want to show that as I get close to c, f of x, is getting close to c. Well, again, I can do a delta epsilon proof. It's, again, pretty trivial. It's given some epsilon greater than 0. I want to show that x minus c is less than epsilon. So what delta do I have to pick? So that this is true? Well, I can just pick epsilon. I can just say delta equals epsilon. Pick delta equals epsilon, then, the function x minus the limit is less than epsilon. Again, it's so simple, it's, kind of doesn't seem to have much point. All right, but we have this tool now. It's kind of a starting point. Let's look at something a little more. Yeah, I think I'm gonna leave off the delta epsilon proofs from here because they're not really necessary. Tool number 3 is given that limit as x approaches c of f of x equals some m, and given some constant k, we have that the limit of k f of x as x approaches c equals k times m. Okay, what does this tell us? It says that when you have limits, you can multiply when you have a function that has a limit, you can multiply the function by a constant, and the limit will be multiplied by that constant. So this allows us to move constants in and out of the limit, which again we'll find useful. All right. Now we're actually getting to something that's going to start to look practical. We have the limit of f of x as x approaches c equal to L, and the limit, now we have two functions, g of x as x approaches c, g of x equals m. We have that the limit as x approaches c of f of x plus g of x is going to equal L plus m. Okay, let's just think about this for a second. We have some function that's like the sum of two other functions, and we want to know what its limit is. Well, if we know individually what their limits are as we get close to this value, we know that the limit of our function is just going to be the sum. So to summarize that, the sum of the limits is the limit of the sum. That's one way to remember it. All right, let's do a real example to actually use this stuff. So what is we have some function here equals x plus 1 for x not equal to 1, and it's equal to pi, I could pick any number, for x equal to 1. We want to know what the limit x approaches, I want to know what the limit is as x approaches 2 of f of x. Okay. Now remember, we don't care what the function is at. I want 2 here. We don't care what the function is at 2. That doesn't matter at all. But we know that this function is the limit as x plus 1 as x approaches 2. If that's the limit, according to number 3 here, that's the limit as x approaches 2 of x plus the limit as x approaches 2 of 1. Well, we have number 2 says that the limit as x approaches 2 of x is 2. And here we have 1, a constant. Well, the limit as we approach 2 of a constant is a constant. Really simple. And the way at least I've defined it, the function isn't even defined. The value of the function at 2 is something else. It's pi, right? Instead of 3. Okay, so that was a nice simple example. Do something interesting. We're going to have a few more rules for finding limits. So let's just enumerate a few more rules that are going to be helpful. Number 5, so give it a label, product of limits. Says if limit as x approaches c of f of x equals L, and the limit as g of x as x approaches c is equal to m, then the limit as x approaches c of f of x times g of x is just going to be L times m. Oh, that's nice. So if I can break up some function into two functions whose limits I know, right, I can then just individually evaluate those limits. Number 6, power of a limit. Well, I'm going to write this out, but if you think about it, you can just apply number 5 and you can get number 6. Right? The way it works is, if we know that the limit x approaches c of f of x equals L, then the limit x approaches c of f of x raised to the power of n is just L to the power of n. N actually could be an integer, or doesn't actually have to be. It could be a real number. This holds just as well. All right. I want to do a kind of a sleight of hand here. I have here that the sum of the functions is the sum of the limits. Just going to slide a minus here. F of x, limit of f of x minus g of x is going to just be equal L minus m in this case. Right? That doesn't really add much. All right. Ran out of room on the board, so I guess we'll start over here. This last rule I'm going to give you today is, again, it's a combination of these other rules, but it's useful. So if we have some polynomial, a to the n, x to the n, plus a to the n minus 1, x to the n minus 1, plus a1x plus a0. Limit as x approaches c of p of x. I'm not going to write it all out, it's just p of c. Okay, so what did I write? 1 here. Should be number 8, number 7. Okay, so we have some rules that tell us, things about limits, and they're going to let us figure out a whole bunch of interesting limit problems. Let's do a few examples here. These are examples. Oh, let's not. Let's take 5 minutes, okay? And then we'll come back, we'll do some real problems, the kind of problems you might have on a homework assignment. The kind of problems you may need for
Yeah.
later in the class.
And because I live in New York, I think about a lot more. So, is there not an assignment?
There is an assignment on their class. No, it's just, yeah, it's like on
I didn't give people a chance at the beginning of class. Were there any questions anyone had on the homework they wanted to bring up? I hope that means it was kind of straightforward. Everybody who did it was all right? All right, good. You know, sometimes, there's anything wrong with it, but sometimes students need to take calculus, and the last class they took was pre-calc in high school. Worse yet, maybe they didn't take calc in their freshman year, put some time between there. And everything you forgot about pre-calc, you'll find out you need in this class. So again, if you haven't done it yet, do the homework. If you have questions on it, either ask them here or come to my office hour. Yes?
I have questions on the folder.
Okay?
Yeah, so on page 44,
Okay. I'm catching up to you. Page 44. Number
45. No, actually 47. But
40
yeah.
47?
Yeah.
Okay. So, first thing I'm going to tell you is that all these problems actually that are like this, in case you don't recall, they're asking you to express this in the form f of g, or f of g of x. In other words, they want you to break this up into two functions. And there's the trivial answer, which is correct for everything, right? I'm going to just, for fun, I'm going to show you. So if f of x is x, g of x is cube root of x over 1 plus cube root of x, you've answered the question, right? Because f of g of x is just what we've got there. That's not what they want. It's correct, but it's not what they want. And it looks like what they want is you say, well, let's make g of x the cube root of x, and f of x equals 1 plus x. So f of g of x would then do this. That'd be more like what they're looking for. But, it's no one right answer here. You could, what else could you do with this? You could say, I thought I had another idea in mind. Maybe you've come up with other answers. Yes?
For f of x, would it be x over 1 plus x? Or would it be 1 over 1 plus x? Like how you wrote it. Wouldn't it be x over 1 plus x?
Oh, thank you. Yes. So, yes.
So then the next one, 48, is everything under cube root. How do you
I'm sorry, say again?
The next one is everything under cube root. So it's x over 1 plus x, the cube root of x over 1 plus x.
I'm missing your point. I'm sorry. Keep going. I'm not very smart in the morning.
Well, that's kind of my question is what's the difference between the two? So the next question, number 48.
Oh, number 48.
Yeah. Yep.
Oh,
Yeah.
I'm sorry. Oh, well, that's a different problem. So, may I erase this? So, I probably shouldn't have, because I think part of the point of having those two is
Yeah.
kind of looks the same. Cube root of x
Same thing.
over 1 plus x. Right, so here, I can say f of x equals the cube root of x. Ah, yeah, they are, just, you just switch them. That's what you meant. Is that what you meant?
I don't know. Is that the right answer?
That would be an acceptable answer, right?
So it's just the
Because
opposite.
f of g of x, right? We just plug x plus 1 into here, and we get what we want.
And to get the other answer, you would do g of f of x of that?
Yeah,
Okay.
but again, the person who wrote the problem wasn't like, they could have said something. I don't know what they could have said to get the result they wanted. But that first result I wrote, you know, is just as true here, right? You can still say, you know, f of x equals x, and g of x equals cube root of x, or
Well,
1.
yeah, the one
That's good too, right? I can't complain. You could monkey with it too. That works. You know. So,
I have another question actually about the homework. It's question 71.
on page 45,
20.
on page 20. yeah.
Correct, yeah. I got the answer all right. It's the volume of the, the shape, the volume of that. But in the back of the book, the answer, it says it has to be, x has to be between 0 and 6. I just didn't really understand why.
Okay, 71. Everyone, I don't know if everyone remembers it. It's, boy, it actually seems like a real practical thing. You might be in the, there's actually an industry. If you have a product and you want to ship it to somebody, there's an industry, there's a companies, you go to them and say, I've got this product, and so, well, show us what it, its dimensions. And they figure out how to take slabs of cardboard and cut them in various ways so that you can pack it and send it, and maybe, I don't know, minimize the waste. Okay, so let's.
I just don't know why x has to be between 0 and 6 though on this question. That's the
Yeah, I haven't gotten there yet. Okay, so they say a box with an open top. Okay. Kind of looks like this. This is 20. And this is 12. And you kind of cut these corners out. Each of these is x. And express the volume as a function of x. Okay. So, here's where spatial relations come into place, right? I think that's kind of what it looks like. So its height is x, right? And this is 20 minus 2x. This is 12 minus 2x. You have to, like, in your head, you have to kind of